We now begin a whole new section of our course, Chemical Equilibrium. This is Chapter 15, but it's going to continue into Chapter 16 and Chapter 17 and take us up until midterms. Let's think about a chemical reaction. Here's a chemical reaction of the type we've written about 1,000,000 times. N2O4 as a gas goes to 2 moles of NO2 gas. Reactants go to products. And as we learned in the last chapter, it does that at some rate and has some rate constant, which is K. And actually that's a lowercase k. That's going to be very important because pretty soon I'm going to introduce a capital K. So rate constant K is a lowercase k. Now, up till now in your entire chemistry education, you have written equations this way. What we've ignored is that actually some chemical reactions go both ways. This particular reaction, for example, also goes in reverse. N2 NO2s actually react together to go back to N2O4. And there is a rate, of course, associated with that, which we can call also K. Now, to distinguish between these K's, I'm going to say this one is K sub F for the forward reaction, and this is K sub R for the reverse reaction. Now, usually, we don't actually write the equation twice. What we'll do is write it once with a double arrow. N2O4 is going to NO2, but 2NO2 is also going back to N2O4. When you see that double arrow, you know the reaction is going both ways. To illustrate this concept, let's take a look at this YouTube video. If you want to look at the whole video yourself, you'll see it's called Bailing Beakers Equilibrium in Chemistry Class. Now, the situation here is you've got 2 students and 2 beakers of water. Both of these students have cups, and with those cups, they are going to bail. She's going to dip her cup in the water, take some water out and put it in his cup, and he's going to take some out of his beaker with his cup and dump it into hers. So that's what we're going to watch right now. Now, ignoring the splashing, take a look at what's happening. The water levels in the beakers are not changing. Aside from some of it that they've lost in splashing, you can see that the level of water in the beakers is practically the same. This is because they were bailing at the same rate. Her speed at which she dumped her water out into his beaker was pretty much the same as at the speed at which he's pulling out his water and dumping it into her beaker. Until she gets a bigger cup. Look at that. The teacher is now giving this girl the bigger cup. Now watch what happens. Now the water levels are changing, right? There's a lot more over here in this beaker that the boy has than there is liquid in the beaker that the girl has. Until we reach the point where the only thing she can lift in her beaker is enough to fill his beaker. Because of that low water level that she's got, she can't get enough in her cup to fill it, And once again, they're taking out the same amount every time. You'll notice the levels are not the same, but those levels will now not change, because once again it's going to be equal the amount that's being taken out of this beaker and the amount that's being taken out of that beaker. So what does that mean in terms of our chemical equations here? Well, if we think back to the kinetics chapter and we call these elementary reactions, then we can say the rate of the forward reaction is equal to the rate constant of the forward reaction times the concentration of N2O4, and we can say the rate of this reverse reaction is equal to the rate constant of the reverse reaction times the concentration of NO2 squared. And remembering the video, the two rates are equal. If I am at equilibrium, the rate of the forward reaction must equal the rate of the reverse reaction. This equation is always true at equilibrium. The rate of the forward reaction equals the rate of the reverse reaction. Okay, so that means we can rearrange this equation to look like this. NO2 squared over N2O4 is equal to a ratio of the rate constants, which in fact is a constant itself. Let's think about that a little more closely. The ratio of rate constants, Kf over Kr, is equal to a constant. We're going to call this constant capital K. This is the equilibrium constant. We're going to call it K sub C because we're talking about the equilibrium constant in terms of concentration. This lovely K we're going to talk about for 3 chapters, and the only thing that's going to change about it is this little letter right here, which is just a label. It's just something to tell you more specifically what kind of reaction we're talking about the equilibrium of. So right now we're talking Kc because we're writing K in terms of concentration. Now in general, if you have a generic equation